Hi, my name is Saket Kenjale, and in today's video we're going to be covering section 2.2, part 2, the limit of a function. And so the first subsection we're going to go over in this part is the existence of a limit. And before we go over this example problem, example 2.7, I wanted to read you something. So it says, keep in mind that for the limit of a function to exist at a point, the functional values must approach a single real number value at that point. If the functional values do not approach a single value, then the limit does not exist. So now let's look at example 2.7, and it says to evaluate limits of sine of 1 over x as x approaches 0 using a table of values. So again, like I said and like I did in part 1, the best way to approach this problem first is to graph sine of 1 over x, and we could do that using a graphing calculator, and for me I'm going to be using Desmos. So now I'm on Desmos and I'm going to graph f of x is equal to sine of 1 over sine of 1 over x. Okay, so as you can see, this is a pretty funky looking graph. It seems pretty normal when we're approaching 0 from the left hand side and approaching 0 from the right hand side, but around 0, at 0, we have this infinitely oscillating pattern going on over here, and you can't even see like what points are there on x is equal to 0. So regardless, let's go ahead and choose the x values we want to use approaching 0 from the left hand side and approaching 0 from the right hand side. So approaching the left hand side, I think that a good starting value would be something like negative 0.1. And so going back to the iPad, I could put in negative 0.1 over here. And then after that, I'll just keep adding a 0. So it'll be negative 0.01, negative 0.001, and negative 0.0001, because we're getting closer and closer to 0 as we go down this list. And for the right hand side, we could choose the same values but just without the negatives. So we have 0.1, 0.01, 0.0001, sorry, 0.001, and then lastly we'll have 0.0001. So now let's go ahead and graph all of these f of x values. So going back to Desmos, we have f of negative 0.1, then we have f of negative 0.01, then we have f of negative 0.001, and finally f of negative 0.0001. And then we'll do the same thing for the right hand side. So we'll have f of 0.1, then we'll have f of negative f of 0.01, then f of 0.001, and finally f of 0.0001. Okay, so now let's graph this back on the iPad, and so let's do that. So for f of negative 0.1, we have 0.5440211108889. For negative 0.00, so for negative 0.01, we have 0.50636564111. And then for f of negative 0.001, we have negative 0.826879509540, and it keeps going on, but I'll stop there because I ran out of space. And lastly, for f of negative 0.0001, we have 0.30561443, then a bunch of 8s. And so now let's graph the f of x values of this right hand side. So f of 0.1 is negative 0.5 440211108889, but I don't have space, so I'll just keep going. F of 0.01 is negative 0.5063656411. And lastly, we have, well, sorry, not lastly, but two more. We have f of 0.001, and that is 0.8268795, and it keeps going on. And then we have f of 0.0001, which is negative 0.305614 and then a bunch of 8s. So looking at our values over here, as we go down from the x values, and approach 0 from both the left and the right hand side, we could see that we're not really approaching an exact value. We're not really approaching a single real number. So from both sides, both this left hand side and this right hand side, we're approaching pretty different numbers over here. Well, at least in this case, at 0.0001, at negative 0.0001, we're approaching negative 0.3056, and f of 0.0001, we're approaching negative 0.3056. So we're not approaching the same number. So because that is the case, the limit of sine of 1 over x as x approaches 0 does not exist. So the value does not exist because we're not approaching a single real number. Now let's look at one-sided limits. So sometimes indicating that the limit of a function fails to exist at a point does not provide us with enough information about the behavior of the function at that particular point. So for example, let's look at g of x, which is equal to the absolute value of x minus 2 all over x minus 2. And so this is the graph of g of x, this is g of x, and as we could see, g of x is actually not defined at x is equal to 2, so g of 2 does not exist, there's no value, and we could see that as we're approaching 2 from the left hand side, we're actually approaching the value of negative 1. We're actually approaching the value negative 1. And as we're approaching 2 from the right hand side, we're actually approaching the value 1. So since the two values, 1 and negative 1, are not equal to each other, we say that the limit as x approaches 2 of g of x, that does not exist. It doesn't exist. And so now I'm going to introduce one-sided limits which help us gain information about the behavior of the function at a particular point. So keep in mind that the original / the general function of a limit is the limit as x approaches a of f of x, which is just any function, that's equal to L, which is any real number. So this is the general function. And now let's look at the two types of one-sided limits. So the first type is the limit of f of x as x approaches a, and then we have this little negative sign on top of a, and that indicates that it's coming from the left side. The limit of x approaching a from the left side of f of x is equal to L. And so in this case, erasing some of the stuff I did over here, in the case of g of x, the left-hand limit, so as we're approaching 2, this is 2, as we're approaching 2 from the left-hand side, we're actually approaching the value of negative 1, because this is negative 1 over here. And so the left-hand limit, which is indicated by LHL, like I said over here, is equal to, we see the left-hand limit, the limit as x approaches 2 from the left-hand side, which is that little minus sign over there, of g of x is equal to -1. So now let's look at the second one-sided limit, which is the limit of f of x as x approaches a, and we have this plus above the a now, and that indicates that it's coming from the right-hand side. So looking at the case of g of x, we see that as we're approaching 2 from the right-hand side, we see that we're actually approaching the value 1. We're approaching this value 1 over here. So we say that the limit as x approaches 2 from the right-hand side with this plus over here of g of x, that is equal to 1. So although in this case the limit does not exist in general, we could find the values, we could find the real number values of the one-sided limits. So now let's look at example 2.8, and it says for the function f of x, which is equal to x plus 1 if x is less than 2, and is equal to x squared minus 4 if x is greater than or equal to 2, it asks us to evaluate each of the following limits. So first it wants us to find the limit of f of x as x approaches 2 from the left-hand side, and it wants us to find the limit of f of x as x approaches 2 from the right-hand side. So let's go ahead and do that, and first let's draw a graph of f of x. So this is our graph, and we'll say that this is 2, so this is 2, and it keeps going, and so this is 1, and first we have the graph x plus 1 while x is less than 2. Okay, so we know that x plus 1 passes the point 0, 1, so passes this point, so it goes all the way up to 2. So it goes all the way up to 2 over there, and we have this function like that. It has a straight line that goes like that, and it approaches 2, and approaches 2 at the point 2, 3, because if you were to plug in 2 in the function x plus 1, you would get 3, so that's its y value. And so now going on, let's find the second part of our function, which is x squared minus 4 as x is greater than or equal to 2. So plugging in f of 2 in our function, we will get 2 squared, which is just 4 minus 4, and that's just 0. So we have 0 here, and then solving for f of 3, we will have 3 squared, which is 9, minus 4, and that's just 5. So we have 1, 2, 3, 4, 5. So we have 3, 5. And we already know that this is a upward facing parabola, so we could just finish this curve over here, finish the curve, and it goes all the way up to infinity. So this is our function. And so now we have to find the limit of f of x as x approaches 2 from the left-hand side and as x approaches 2 from the right-hand side. So looking at the left-hand side first, we see that as we're approaching 2, we're getting closer and closer to the value of 3. We're getting closer and closer to the value of 3, but we actually don't have an existing value at 3. But that's what the limit is. So we say that the limit, so this is a, the limit as x approaches 2 from the left-hand side of f of x is equal to 3. And then for b, the limit as x approaches 2 from the right-hand side of f of x, well, let's find that out. So as we're going down, all the way down, and we're getting closer and closer to 2 on the x-axis, we're getting closer and closer to the value of 0. So that's why our right-hand limit as x approaches 2 is equal to 0. And now we're done with this problem. Now let's look at our first theorem of section 2.2. So it says, let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself, and let L be a real number. Then the limit of f of x, so if the limit of f of x as x approaches a is equal to L, that is only true if and only if the limit of f of x as x approaches a from the left-hand side is equal to L, and the limit of f of x as x approaches a from the right-hand side is equal to L. So if the left-hand limit and the right-hand limit are equal to each other, only then is the limit of f of x as x approaches a equal to L. Now let's take a look at infinite limits. So let's take a look at h of x, which is equal to 1 over the quantity of x minus 2 squared. And so this is the graph of h of x. This is h of x. And as we can see, as x approaches 2 from the left-hand side, we're going all the way up and up, all the way to infinity. We're going all the way up to positive infinity. And as we approach 2 from the right-hand side, we could see that we're still going all the way up to infinity as well. So we could say that the limit as x approaches 2 of h of x, that's equal to positive infinity. And some mathematicians actually notate it like this, but in reality, because infinity is not a real number, it's not a real number, we don't actually notate it like that. And in reality, the limit as x approaches 2 of h of x, we say that it actually does not exist because infinity is not a real number. So now let's look at 3 types of infinite limits. So first, we have the left-hand limit, which is similar to the one-sided limits that we talked about. So the limit as x approaches a from the left-hand side of f of x can be a positive infinity. So this left-hand limit can be a value like infinity. It doesn't have to be a real number. And also we could say that the limit as x approaches a from the left side of f of x can be equal to negative infinity. We could also write it as negative infinity in the case that if you were to imagine that this graph was actually going down to negative infinity, this would be negative infinity over here. This would be negative infinity over here. Our second situation is the right-hand limit. And again, we talked about this in the one-sided limits, where the limit of x approaching a from the right-hand side of f of x is equal to positive infinity, or the limit of f of x approaching a from the right-hand side is equal to negative infinity. And again, the same case over here. Like so, this would be the left-hand limit. The left-hand limit would approach negative infinity, and the right-hand limit would approach negative infinity. So that would be the case of these negative infinities over here. And our last case, our third case, is the two-sided limit, saying that the limit of f of x as x approaches a is equal to positive infinity, and the limit of f of x as x approaches a is equal to negative infinity. We can write it like this, but I put this little asterisk over here because this is actually not a correct way to say it, but you are allowed to notate it like this. So in this case, in the case of h of x, the limit as x approaches 2 of h of x is equal to positive infinity. So we could write it like this, but it's not actually the correct way to put it. So it's not correct, but we can write it like this to get a better sense of the behavior of the graph as x approaches 2. Now let's look at example 2.9, and it says to evaluate each of the following limits if possible. Use a table of functional values and graph f of x is equal to 1 over x to confirm your conclusion. So A, we have to find the limit of 1 over x as x approaches 0 from the left-hand side. Then we have to find the limit of 1 over x as x approaches 0 from the right-hand side. And then we have to find the real total limit of 1 over x as x approaches 0. So now let's go back to Desmos and graph f of x is equal to 1 over x. So now I'm on Desmos, and now let's graph f of x is equal to 1 over x. And we can see, zooming out over here, that at x is equal to 0, there's actually no point defined over here. And so, looking at a, the limit as x approaches 0 from the left-hand side of f of x, we see that as we're approaching 0 from the left-hand side, we're getting closer and closer to, zooming out here, we're getting closer and closer to negative infinity. We just keep going down to negative infinity. So that is our value for part A. So let's go back to the iPad, and we could conclude that the limit as x approaches 0 from the left-hand side of 1 over x is equal to negative infinity. And now let's go back to Desmos and look at part B. So looking at the limit as x approaches 0 from the right-hand side, looking at all of these x values, we see that we're shooting up and going straight up to infinity. So zooming out and going up, we can see that we're going all the way up to infinity. So going back to the iPad, we can say the limit as x approaches 0 from the right-hand side of 1 over x, that is equal to positive infinity. And then lastly, for part C, we could use the table of functional values to solve for the limit as x approaches 0 of f of x. So going back to Desmos, let's zoom out and go back to the center again. So let's choose some good x values approaching 0 from the left-hand side. So let's choose negative 0.1. We could choose negative 0.1, and then we could just keep adding a 0 like we've been doing. So going back to the iPad, we could choose negative 0.1, negative 0.01, negative 0.001, and negative 0.0001. And for the right-hand side, we could just do the same thing with the positive values. So negative 0.1, negative 0.01, negative 0.001, and negative 0.0001. And now let's solve for the f of x values going back to Desmos. So f of negative 0.1, as we can see, is negative 10. And then let's just keep going. F of negative 0.01, f of negative 0.001, and f of negative 0.0001. And now let's do the same thing for the right side. So f of 0.1, we can see is 10, f of 0.01, 100, f of 0.001, 1,000, and f of 0.0001 we see is 10,000. So now let's plot all these values back onto our iPad. So going back, f of negative 0.1 is 10, next we have 100, then we have 1,000, then we have 10,000. And this is all negative, sorry, this is all negative. So negative 10, negative 100, negative 1,000, and negative 10,000. For our right hand side, we have 10, 100, 1,000, and 10,000. So as you can see, as we're getting closer and closer to 0 from the left hand side, we're getting closer and closer to negative infinity from the left hand side. And as we're getting closer and closer to 0 from the right hand side, we're getting closer and closer to positive infinity. So as you can see, the left hand limit and the right hand limit is not equal to each other. So the left hand limit is not equal to the right hand limit. So therefore we say the limit does not exist. So going back up to C, the limit as x approaches 0 of 1 over x does not exist. So now we're done with example problem 2.9. Now let's look at this useful tip. So functions in the form of f of x is equal to 1 over x minus a to the power of n, where n is a positive integer have infinite limits as x approaches a from either the left or the right. And so we can see that h of x in our last couple of examples, h of x is in this form. So in this case, this minus 2 over here is a, and this squared 2 over here is n. And also, in example 2.9, this is also in that form. So it's just that a in this case is 0 and n in this case is 1. So this right here, let's look at these two graphs over here. So this graph on the left is an example if n is an odd positive integer, and the right hand graph is the example if n is an even positive integer. So that is an important, useful tip. So now let's look at our next theorem of section 2.2. So if n is a positive even integer, then the limit as x approaches a of 1 over x minus a to the power of n is equal to positive infinity. And keep in mind that these two a's are actually different. They're not the same a. If n is a positive odd integer, then the limit as x approaches a from the right hand side of 1 over x minus a to the power of n is positive infinity, and the limit as x approaches a from the left hand side of 1 over x minus a to the power of n is negative infinity. So a quick note over here, the line x is equal to a is a vertical asymptote of f of x. Like in these two cases over here, this is the line x is equal to a, and this is also the line x is equal to a. Now let's look at example 2.10. So it says to evaluate each of the following limits using infinite limits from positive integers. Identify any vertical asymptotes of the function f of x is equal to 1 over x plus 3 to the power of 4. So notice that this function is actually in the form f of x is equal to 1 over x minus a all to the power of n. So n in this case, n is equal to 4 and a is equal to negative 3. So let's erase this. And now let's look at our parts that we have to solve for. So part A, the limit of f of x as x approaches negative 3 from the left hand side, limit of f of x as x approaches negative 3 from the right hand side, and the limit of f of x as x approaches negative 3 in general. So n is equal to a positive even integer. And so looking back at our theorem that we just learned about, so in the case that n is a even positive integer, then the limit as x approaches a of 1 over x minus a to the power of n is equal to positive infinity. So that means that this limit for part A is equal to positive infinity. This limit for part B is equal to positive infinity. And obviously infinity isn't a real number, so the limit as x approaches negative 3 of f of x does not exist. And lastly, identifying any vertical asymptotes, we see that x is equal to negative 3 is a vertical asymptote. So vertical asymptote, abbreviated as VA, is our vertical asymptote for this function. Now let's look at the last example problem of section 2.2, example 2.11. So reading it, it says, use the graph of f of x in the figure below to determine each of the following values. So let's look at this figure over here. So we could see that it goes up to negative 4, then it goes up to negative 6, and then it breaks, and then we from 3 we go down to negative infinity, and then we go up to 3, close to 3, and then we go all the way up. So looking at A, they want us to find the left-hand limit of x approaching negative 4 of f of x. So as x approaches negative 4 from the left-hand side, we see that is actually equal to 0. It's actually equal to 0 over there. So our answers will be 0, and I'll put a semicolon. Then for the second part of part A, the right-hand limit. And so again, looking as we go down to -4 from the right-hand side, it is still 0. So it's 0 again. And the regular left-hand limit is still 0 because the left-hand limit and the right-hand limit approach the same value L, and in this case L is 0. So that's why the limit of f of x as x approaches -4 is still 0. And if we were to find f of -4, we would see that it's still 0. It's still 0. So we have zeros across the board for part A. Looking at part B, we have to look at the limit of f of x as x approaches -2 from the left-hand side. And so -2 over here, we see, let me erase these arrows over here. And going back, the left-hand limit, as we approach -2, we see that we approach the value 3. We approach the value 3 over here. So that's why our first answer is 3. Looking at the second part of part B, we see that they want us to find the limit of f of x as x approaches -2 from the right-hand side now. So looking at the right-hand side, it still approaches the value 3. Looking at the third part of part B, we see that they want us to solve for the limit of f of x as x approaches -2. And since the left-hand limit and the right-hand limit are both equal to each other, as we can see over here, the left-hand limit and the right-hand limit are both equal to each other, then the limit exists and is equal to 3. Now, finding f of -2, as we see here, we actually see that there's a hole at f of -2, and so f of -2 does not exist. So now let's look at the first part of part C, the limit of f of x as x approaches 1 from the left-hand side. So again, I'm going to erase these arrows. And so the limit as x approaches 1 from the left-hand side, we see that we start off from here and we approach 1 from the left-hand side, and we see that we get a value of 6. So we get 6. Looking at the second part of part C, we want to find the limit of f of x as x approaches 1 from the right-hand side now. And as we can see, as we start from the right-hand side, we get closer and closer to 1, we actually approach the value 3. So we approach 3. And next, solving for the limit of f of x as x approaches 1, we realize that the left-hand limit, which is 6, and the right-hand limit, which is 3, are not equal to each other, so therefore the limit does not exist. And finally, the fourth part of part C, f of 1. And as we can see, this dot right here is filled in all the way, so we could see that f of 1 is actually equal to 6. So that is it for part C. Looking at part D, the first part of part D, we see that the limit of f of x as x approaches 3 from the left-hand side. Again, I'm going to erase these arrows. So approaching 3 from the left-hand side, we go down to -infinity. So this is -infinity for the first part. The second part wants us to do the same thing, but for the right-hand side. So going down and getting closer and closer to 3 from the right-hand side, we're still going to -infinity. So this is -infinity. The third part, they want us to solve for the limit of f of x as x approaches 3. And we know that even though the left-hand limit and the right-hand limit are equal to each other, they're both -infinity, they are not real numbers. So therefore, the limit as x approaches 3 of f of x does not exist. And looking at our final part, f of 3, find f of 3, we notice that it also does not exist because these values are approaching -infinity and there's no real number. So again, it does not exist. And now we're done with example 2.11. So this is it for part 2 of section 2.2, the limit of a function. If you enjoyed this video, please be sure to like the video and subscribe to my channel to see content that is similar to this. Thanks, and I'll see you in section 2.3, which is the limit laws.